Hi there. My name is Randy Bryant. I've been involved in automated reasoning for many years, but my most recent interest has been in Boolean satisfiability, or actually in unsatisfiability, and I'll explain to you what I mean by that and why it's an important problem. So in the lectures I'm giving, there's a few themes that I'd like to convey. First of all, Boolean satisfiability solvers, which are just called SAT solvers, are very powerful tools with many applications. Even though they just deal with the lowest form of logic, propositional logic, many practical problems can be reduced to that form. And there's a collection of very powerful tools to apply to these problems. For a lot of real-world applications, it turns out the case that the formula is unsatisfiable is more interesting or more important than when the formula is satisfiable. And I'll show you some examples of that. And one important task then is, if the formula is really unsatisfiable, how can we make sure that's really the case and it's not just some bug in the SAT solver? I'll also talk about binary decision diagrams and how they can be used in combination with other approaches to SAT, and in particular, how they can be used to help generate proofs of unsatisfiability. So imagine you're a manager at a startup company, a software company, and one of your new employees comes to you and says, I have this great new way of computing absolute value of an arbitrary int x, and it doesn't involve any conditionals. It just involves bit operations, and so it's going to be really efficient. And you say, well, I don't know. Is it really true? Are there some exceptions? How do I know? First of all, you recognize, wait, this isn't going to be true in arbitrary cases. I must assume that it's a 32-bit number and that I'm representing signed integers in 2's complement form. But beyond that, is it true for all possible 2 to the 32 combinations of x then? Well, we could set up a testing framework where we generate an arbitrary value t, and we evaluate our new function abs new and our reference function abs ref, and say if it produces different results, then we'll flag that as an error. And now the question becomes, can an error occur? Or in particular, can you show me that an error will never occur? There's a program that's widely used in industry called C-bounded model checker that was first developed by my colleague Ed Clark and his postdocs back in the early 2000s. The idea of it is to take a C program and turn it into a SAT problem. This only works for fairly short C programs. But the idea is to expand this code into a massive Boolean formula where we're representing every single bit and how it gets changed or operated as the program proceeds. And we'll assume that any loop is going to be a bounded number of executions, so we can simply unroll it to whatever its maximum is. And so this becomes essentially a large Boolean circuit, and we set up the error condition as the result that the formula will be satisfiable if this error can occur. And so now what we're asking is this formula unsatisfiable? And if it is, can you actually prove to me in some concrete way that that's the case? On the mathematical side, there is an open problem called the Pythagorean triple coloring problem. And this problem was open until 2016. So a Pythagorean triple are 3 integers, say 3, 4, and 5, so that they could form the sides of a right triangle. And we'll say that there's a 2 coloring of these set of triples if for all possible Pythagorean triples with numbers less than or equal to n, for any given triple, we won't assign the same color to all 3 of those numbers. And so you can see, obviously, like if n is 5, there's only 1 triple, and it's colorable, so that's fairly trivial. But as n grows larger, the question is, do we start throwing in so many possible of these triples that the problem becomes impossible to color. And the answer to this was not known until relatively recently. It's very easy to turn this into a SAT problem. We'll introduce a Boolean variable x sub a for every integer a between 1 and n. And we'll say that it's 1 if we color that number red, and 0 if we color that number blue. And what we'll say is for every Pythagorean triple a, b, and c, then, at least one of them must be red and at least one of them must be blue, given by these two what are called clauses or disjunctions, where we put a line over a variable to mean it's complemented or negated. So for n equals 7824, it's possible using a SAT solver to find a coloring. In particular, this picture shows all the numbers between 1 and 7,824, where red means it must be colored red, blue means it must be colored blue, and white means the coloring of it is arbitrary. And now the question is, well, yeah, but what about larger values of n? Well, for n equal to 7825, a group, including a person who's now my colleague at CMU, Marijn Höhle, was able to show that formula is unsatisfiable. And it's pretty easy to see, by the way, if it's unsatisfiable for some value of n, it will be unsatisfiable for larger values of n as well. The way they did this was to take this SAT formula, which is in some ways very simple and not all that large, and partition it into 1 million different cases by enumerating some of the variables, and then running 1 million different runs of a SAT solver on a supercomputer with many cores over 2 days of execution. And each of those came back with the result saying it was unsatisfiable. And better than that, they actually came back with proofs that they were unsatisfiable. A huge proof, not a very interesting proof either. But by then checking all 1 million of those proofs and combining all that information together, we can claim that we have mathematically proved that this coloring problem is a bounded case. In other words, 7825 is the cutoff between what can be colored and what cannot be colored. So you see, both of those examples were cases where the outcome we were looking for was unsatisfiable. And now we can see we've shown both formal verification and mathematical proofs that SAT solvers are useful, and there are many uses for them in other applications as well. So if a formula is satisfiable, the solver can produce a solution to it, and then we can easily check, is that solution really satisfy the Boolean formula? So that one's fairly safe. But if it's unsatisfiable, then it's open to speculation. What if there's some bug in the SAT solver? It might come back and say the formula is unsatisfiable just because it overlooked a possible solution. And this is indeed a real possibility. These are very complex pieces of software, many thousands of lines of code, filled with very tricky algorithms, lots of optimizations, lots of places where they could make mistakes, and just come back and say, nope, not satisfiable. And we really don't want to trust that, especially if we claim this is formal verification or mathematical proof. What does it mean if we're running it through a possibly buggy program? So the way to handle this is to have the solver produce a proof, a checkable proof, that the formula is indeed unsatisfiable. And this proof should be in a very well-defined logical framework for which we can write a proof checker that will go through step by step and make sure that every inference in that proof is correct. And therefore, the total result is that this formula is indeed unsatisfiable. And that proof checker, hopefully it will be small enough and simple enough that we can write it reliably. Or better yet, we might be able to formally verify the proof checker. And so this shows a general idea. Is imagine we have software that is so complex that we can't possibly verify that it will work in every single case. But it might be possible for every possible result that it produces to formally check that that result is okay. And so imagine, in fact, this is a buggy solver, and sometimes it gets the wrong answer. If it's produced an unsatisfiability proof, and we've reliably checked that proof, then regardless of that bug, any potential bugs, that formula is definitely unsatisfiable. And so that's a very powerful result. So this idea of proof checking was developed in the early 2000s as a way to help the people writing SAT solvers. And starting in 2016, in the annual SAT competition, which has been a major driver of progress in the world of SAT, they required that any entrant would only get credit for an unsatisfiable result if it produced a checkable proof and that proof checked correctly of its unsatisfiability, using a standard framework, standard notation, and so forth. So this really helped the competition. It made it so that they could clearly judge the outcomes, but it's also had a big impact on the developers themselves. If they're developing some new algorithm for their SAT solver, and they start have maybe a bug in it, pretty quickly it will start failing to produce the unsatisfiability proofs that it should be proving. And that will be enough for them to help track down the source of this bug. Also, again, if we're claiming we're doing something mathematically rigorous, we want that firm foundation of a proof. Like every good idea, though, it's had some unintended consequences. One is that it's tended to narrow the focus to a particular class of SAT solvers called conflict-driven cause learning solvers, or CDCL. Now, these are by far the most powerful general approach to SAT solving, and so I don't want to discredit them at all. And we have a proof framework that I'll describe that very naturally makes a good target for this class of SAT solvers. But there are also some other weaknesses of CDCL that we'll also look at, for which there's known algorithms that can help augment the CDCL or replace CDCL and more reliably get results quicker, but for which there were no known techniques for generating proofs. And so these ideas have kind of languished because people knew if they worked on them, they weren't going to be able to introduce them into SAT competitions, so there wasn't a lot of motivation to do so. So my own research for the past 2 years has been to try and overcome this partially, to say, well, what about other approaches to SAT? Are there ways we could better include them in a way that also generates proofs? And going beyond that, I think this is such a powerful idea that I'd like to see applied not just to Boolean satisfiability, but other automated reasoning tools. Can for other tools we produce a proof, that a checkable proof of the outcome of what the tool says for a given formula or problem? As a background then, when we're using a SAT solver, we express Boolean formulas in what's called conjunctive normal form, or CNF. And you can think of this as a very simple product of sums form. So we'll say that there's a set of Boolean variables, x1 through xn, or informally I'll just use names like a, b, and c, because it's easier to keep track of those. And for each variable, we can represent either the variable in its true form or its complemented form. And we'll call those two cases literals. And we'll use the line over a variable to indicate its complement. So a clause is then a disjunction of literals, or a set of literals. And I'll write it in disjunctive form. A particularly important clause is one with no literals, the empty clause, and that cannot be satisfied at all. So if that's in a formula, or as we'll see, if that's generated by a proof, that's an indication that the formula is unsatisfiable. Finally, a formula itself is just a conjunction of clauses, and I'll write that as a set of conjunctions. As I mentioned, it's been the last 2 years I've been heavily involved in this, and one thing I had to develop was more skills for how to translate a problem into CNF. And I've learned a few tricks that I think might be helpful. One is, I find it much easier to think in terms of implication than to just spit out something in pure CNF. So as this first example shows, if I have something like A and B implies C, I can directly convert that to CNF by complementing the first two variables, what are in the antecedent of that implication. And similarly, if I have a disjunction in the consequent, I can just put those directly into the CNF. On the other hand, if I have an antecedent which is a disjunction, then I have to generate two separate clauses. One is A implies C, and the other is B implies C. And similar, if there's a conjunction in the consequent, that turns into two or more clauses. A implies B, and A implies C. A particularly common case that sometimes is referred to as the ITE, or if-then-else operator, is we want to write, if A is true, then B, otherwise C. And so we can think of this as the conjunction A implies B, and not A implies C. And so we can write that as a pair of clauses as shown. I think you'll find other simple examples. If you just think in terms of implication, you'll get these more reliably than if you just try to create raw, pure CNF. A particularly common kind of constraints we might look at are parity constraints. Is this set of variables, if we compute their exclusive OR, would it yield 1, meaning odd parity, or 0, meaning even parity? In general, what we have to do for this is to enumerate all possible combinations of A, B, and C, or the variables being in true or complemented form. And we list for odd parity all those that have an even number of negations, and for even parity, all those that have an odd number of negations. Sounds odd, but that's the right way to do it. The problem we see here is that this is an exponential encoding. As we add more and more, in general, if we have n variables and we want to express a parity constraint, it's going to take 2 to the n minus 1 clauses. So there's a trick when this occurs. If we have, say, n equals 100, we really don't want to write this as 2 to the 100th clauses. So there's a trick that we can use where we recursively expand this by introducing intermediate or auxiliary variables. And so we can express it in the following way. Imagine I have n Boolean variables, and I want to compute their odd parity, or express that as a formula. Then I'll just take the first two, x1 and x2, and I'll introduce a new variable, I'll call it z here, and generate a formula for the even parity of x1, 2, and z, and then just the odd parity of z and the remaining variables. And I claim that's the odd parity of x1 through n. And that includes the case where I recursively expanded the second case. So what you can think of it is, if x1 and 2 have even parity, then z will be 0. And if x1 and 2 have odd parity, then z will be 1. So since z is encoding the parity of x1 and 2, and I'm inserting that into this odd parity constraint, saying that it plus the remaining ones have to be odd parity. And that continues holding throughout my expansion. So if I took n variables and I applied this recursively over and over again, I'd introduce n minus 3 total variables, z2 through zn minus 2. And what I'd have is a linear expansion where each z sub I depends on its preceding z sub I minus 1 and one of the variables, until I come to the very end, and then the final z plus the remaining last two x's I get as a single odd parity constraint that I can encode directly. So you can see this reduces the total number of clauses to something linear. So it's very practical to do these kind of things in CNF. Another class of very useful constraints are what are called cardinality constraints. So imagine I'm doing integer arithmetic or integer inequalities, except in this case I'll require that x1 through n all be 0 or 1 value. This is sometimes called a pseudo-Boolean formula. And in this case, let's just consider the case where the a's are either 0, 1, or -1, as well as t. So for the first case, if I just have 0 and 1, and t is 1, that is saying at least one of the x's must equal 1. If I have the a sub i's being 0 and -1, and the threshold t being -1, it's saying at most one of them is -1. And both of these are fairly useful constraints. So to encode this in CNF, we can see that at least one is just the disjunction. That's very straightforward. At most one's a little bit trickier. And the standard, or what's called the direct encoding of that, is to just say for any pair of x's, one of them has to be false. In other words, they can't both be 1. And if you do that for all combinations, you can see that that's overall putting in this at most 1 constraint. You can see if I add from 3 to 4, have to add more and more of these, and it grows quadratically in n, which isn't as bad as exponential, but quadratic still can grow quite a bit for real life cases. And in general, imagine I have an arbitrary Boolean circuit, or in general a Boolean formula, and I want to encode that in CNF. Then the same encoding trick that I showed for the parity constraints works here too, and allows me to express it with a linear number of clauses. So in particular, imagine a NAND gate followed by an OR gate. I'll introduce what's known as a Satan variable, and I'll tell you where that comes from, to represent the different values or different positions in the circuit, or the different subformulas in my larger formula. And I'll just, for every logic gate then, require that output matches the appropriate Boolean function applied to the inputs in both directions, an if and only if direction. So for example, I say T1 bar if and only if x1 and x2. You can see I get complements for free in this encoding. And similarly, z if and only if t1 or x3. And each of those then turns into 3 clauses. And the combination of those two then is providing the overall constraint that z if and only if x1, x2, and x3. And you can see that I can do this for any formula and it will be of linear complexity. So this is a very widely used trick. The standard rule for doing proofs in propositional logic is what's known as the resolution principle, which was devised back in the 1960s. And there's a very simple syntactic way of describing it. You say, if I have 2 clauses that differ from each other by exactly where there's a true variable in one and its complement in the other, then I can form a new clause by taking the other variable literals in the 2 clauses and concatenating them together. To me, I knew this rule, I've heard it many times, and it just looks like a bunch of syntax. So can we understand better what the underlying logic of this principle is? Well, yes, we've learned about implication. So in particular, we now know that the left-hand formula can be written as A and B bar implies X. And the right one can be written as X implies C or D. And so what we're really doing is using transitivity to say A and B bar implies C or D bar, which is what the resulting clause, the so-called resolvent, expresses here. So you can think of resolution then as a form of implication. And in particular, if we string together a long sequence of resolutions, what we're just doing is using the transitivity of implication to show that the leftmost antecedent implies the rightmost consequent. There's a few cases that are important to understand in resolution. One is, it's all right to have the same literal appear in both parts of the resolution, in this case B. But it's not okay to have a variable in its complement. There can only be one variable in the two clauses that appears positively in one and negatively in the other. Otherwise, the result is just a tautology, meaning we're not adding any new information. We can't derive any new information from this pair of clauses, through resolution at least. A final rule that's sort of implied or overlooked is subsumption, which is just a statement that if I prove something F and I allow more possibilities like disjunction with D, well, that result still holds. So let's take an example of a Boolean formula, which is shown in here by 6 different clauses over variables A, B, C, and D. The standard way to encode this to a SAT solver is a file format called DIMACS, named after a series of workshops that were held at Rutgers in the late 1990s. So the DIMACS encoding is a very simple low-level encoding where you kind of lose all the information about the formula, but it works well for automated tools. Instead of giving names to variables, I'll just number them 1 through n, and I'll use +1 to indicate that variable, or -1 to indicate its complement. And then I'll list clauses, and I'll terminate each sequence of literals, or positive and negative numbers, by a 0 to mean the end of this clause. And at the beginning, I have a header that says P, C, and F, meaning this is a CNF file, with 4 variables and 6 clauses. So I can take that file and feed it into a SAT solver and see what I get. And what you'll find is it's unsatisfiable. And what you can show is, through a resolution proof, that it is indeed unsatisfiable, meaning through a series of resolution steps, I can derive the empty clause. And since I can derive that clause as a consequent through a series of implications from the original set of clauses, it must mean that that set of clauses is unsatisfiable. The only thing that's a little odd in my notation is I have to use the resolution of one of the resolutions twice. So I show that with the resolution result A being used twice. But you'll see now if I step through this, I'm just on each level applying one step of the resolution principle to get it down to the case, the final case. I'm saying one side gives me B and the other side gives me B bar. I resolve that by removing the resolution variable B, and I end up with the empty clause. So that's a rigorous proof that this set of clauses is unsatisfiable. But how can I get that? What kind of tool can generate those proofs? And how can I make this automated? And how can I implement proof checkers based on that? Well, the checking part is pretty straightforward. You just make sure that each step obeys this resolution rule. But how did I generate that? Well, that's something to discuss in our next lecture.